Okay, hope you're doing well. Dugan Ashley here. Second installment of the energetic series with Dugan Ashley. We are talking about nitroguanidine. This is a hard video to make. I've tried it like 3 times and nothing seems to go right. So somehow I am jinxed on nitroguanidine, but we're going to do it this time, I promise. A little bit on the history of nitroguanidine. It was found in 1877. That would be Jocelyn that found it. He mistook it for a nitroso. That's incorrect. It's not a nitroso. They didn't figure out the identity of nitroguanidine for quite a while, so they were disagreeing on its identity up until at least the 50s. First use of it in terms of industrial use, you would have had wartime Germany, World War II, using it in armor-piercing shells. So the theory behind that is that you would bypass armor, detonate on the other side. Nitroguanidine is something that's so insensitive you can actually get away with doing that. Post-World War II, interest in nitroguanidine, it drops off pretty considerably as a conventional munition. The production of Tat B really kind of takes place of insensitive munition needs, and nitroguanidine is kind of forgotten. There was a time when the Army, I think, was going to make a nitroguanidine production facility in the 70s. They ended up not doing it. I think it was going to be based off BMR process, which is like a urea, ammonium nitrate, and silica gel process to produce guanidine nitrate that then gets turned into nitroguanidine. Anyways, they didn't do it. They didn't make the production facility. They probably should have, because as of right now, the most current up-to-date insensitive munition formulae all involve nitroguanidine. So that'd be like all of your Air Force explosive, that's AFX series, IMX series, aluminum IMX series, all of that stuff is going to incorporate nitroguanidine as an ingredient. So that is the modern use, is insensitive munitions, typically dumb bombs, large payload, 500-pounders, Mark 82s, stuff like that. That's going to include loads of nitroguanidine. It's difficult to say, but I think nitroguanidine is probably more insensitive than Tat B, and it's way less exhaustive to produce in terms of materials and time. It's just a lot simpler of a synthesis than something like Tat B. But in terms of the difference between the two, Tat B is way higher temperature. So for cook-offs or decomposition, when missiles or bombs are caught in a fire or something like that, Tat B has a little bit of an edge over nitroguanidine, but nitroguanidine is still a pretty high decomposition temperature. It's actually a range, it's 220 to 257 C, and that depends on the rate of heating. It decomposes without melting. The other modern use I'll mention is propyl nitroguanidine. So if you hit nitroguanidine with propylamine, you can produce a propyl extension that drops the melting temperature down to below 100 C, which is excellent. And milk cask carriers like TNT, this would be an alternative to TNT. That stuff is probably more needed than anything else in terms of energetics research or additional milk cask carriers. So that's the case of industrial production and munitions production, things like that. That's how they're going to use it. For an amateur energetics capacity, it's going to be a lot different. Nitroguanidine, I would consider it to be an advanced material in use case. So in production, it's pretty simple, it's straightforward and easy. In use case, it's pretty complex. And that has to do with the variability of the character nitroguanidine, which totally depends on the density. Okay, so to give you an example of what I'm talking about, when you produce nitroguanidine, it's usually going to be in large needle crystals. It's going to be a felt matte type of consistency to the feel. This is low density nitroguanidine. It's going to be somewhere around 0.3 grams per cubic centimeter, and that's considered hand pack density is what they call that. That's what most people are going to be familiar with. Now, if you go to the high end of it, 1.78 grams per cubic centimeter is going to be max density of nitroguanidine. The performance between those two densities is really wide, both in pressure and velocity. In terms of velocity, on your low end, when you get to hand packed, it's like 2.8 kms, which that's similar to like ammonium nitrate detonation. And at the high end, 1.78, you're going to be over, well over 8, so you'd be like 8.5 kms. For pressure figures, if we go up to, I can reference this at 172, you're getting 24.5 GPa, which is excellent. That's very good. RDX is in the 30s, so anything 20 plus is great. And so with max density nitroguanidine, you're getting almost the performance and velocity of RDX, and you're getting a pretty decent pressure too. So it's a very usable explosive at high density. It's very difficult to achieve that high density at 178. I mean, when you're precipitating nitroguanidine, you're going to be at the 0.3 hand pack density. And I mean, it's going to be low performance. So for pressure, even at 1 gram per cubic centimeter, which is higher than 0.3, obviously, 4.2 GPa, which is pretty low. It might be usable, but it's going to be low performance compared to max density nitroguanidine. For that reason, it just makes sense to use a melt gas carrier. You can up your density when you melt nitroguanidine into it. The most common of those is by far TNT, which would be, that's known as Nitutol. And Nitutol has different formulations, but if you get up to 85% nitroguanidine content, that is where you get the highest performance. You're going to be over 8 kms of detonation velocity, which is very good. It's over baseline performance of something like Comp B. For amateur energetics, TNT is kind of avoided. What's more common is to see other molecules derived from nitroguanidine. So we just did NAP. Well, that uses aminoguanidine. Aminoguanidine can be reduced from nitroguanidine. You can also make stuff like ANQN, that's amino nitroguanidine nitrate. It's super high energy. You're going to be at 9.5 kms det velocity. That's extremely high. That's derived from nitroguanidine. Your oxygen balance for CO2 is going to be negative 30.75. It's very oxygen deficient. Critical diameter, you need to be making charges if you're using this above 14 millimeter. When you start to get below 14 millimeter, you get diminishing returns. You get something called detonation fade out. So you want to stay above 14 mil diameter. Let's talk about synthesis of nitroguanidine. The best way known so far is to treat guanidine nitrate with sulfuric acid. That is the common procedure. This used to be known as a dehydration reaction. That's actually probably incorrect, and it stems from them misidentifying the molecule. It's not really a dehydration reaction. It's more a classical nitration and using a nitrate salt with sulfuric acid to produce nitronium ions. Because it's a guanidinium ion in the center here that you're treating, you get an iminium nitronate on the top, and that's what is responsible for nitroguanidine's insensitive character. If nitroguanidine is a classic nitration and not a dehydration, then it should follow all the same rules as a classic nitration. That's exactly what it does. Guanidine nitrate itself can be used as a nitrating agent for other materials, and you can increase reaction rate by giving it more nitrates into the reaction. This is the problem with the classic procedure where you're only using guanidine nitrate and sulfuric acid. There's only one nitrate available for each guanidinium ion. And what you're trying to achieve here is adding an iminium nitronate on the top of the guanidine. By adding additional nitrate availability, you can increase the reaction rate and the total yield at the end of the reaction. So here's how I play with nitroguanidine. I reference McKay papers from the 1950s. He's got a really good overview on synthesis methods that he's used. Probably the most successful would be Smith, Sabetta, and Steinbach. They figured out that if you increase sulfuric acid to 3:1 on the ratio to guanidine nitrate, you up your yields. They're getting 92% repeatedly. Now they are doing a reaction time of 60 minutes. That's what I do. I do 60 minutes. Their temperature is about 0°C, which is pretty low. It's aggressive. I don't usually do that just because it's impractical for the quantity of nitroguanidine I'm usually producing. But I do borrow the reaction time of 60 minutes, 3:1 sulfuric acid to guanidine nitrate ratio, and then I add in ammonium nitrate as additional nitrate availability to increase reaction rate and the yield. I've experimented with even at room temperature, you're going to get increased yields with addition of ammonium nitrate versus not. I add ammonium nitrate at about 20% of the molar weight from your guanidine nitrate you're using. Keep in mind, if you're using a OTC drain opener as the sulfuric acid source, those aren't 100%. So I'm using I typically use a Santeen or something from Menards. Those are 85 to 87% usually. I use for nitroguanidine production or for anything that's difficult to stir, like a nitrate ester or something like that, I use an overhead stirrer, typically with the PTFE paddle. They work great. It's way better than a magnetic stirrer. I would definitely recommend it. Starting off the reaction, you probably want your temperature of your sulfuric acid cooled. You can cool it in the freezer if you want beforehand. Don't leave it in there too long because sulfuric acid can freeze. But you want it pretty cool. You can freeze your guanidine nitrate to get it cold right off the bat. You want to start at around 0 to 5°C is a good temperature range for beginning. You slowly begin adding guanidine nitrate. Your temperatures are going to raise. You want to try to keep things below 40°C. A good working range is up to 20°C. Keep in mind, the higher that your temperatures go, the lower your yields are going to be. So ideally, if you could stay at 0C the entire time, that would be best. But in terms of just getting a yield, it's extremely forgiving as a reaction. You can really get sloppy with this thing and still get decent yield. So once you get all of your guanidine nitrate and ammonium nitrate added to the sulfuric acid, and it all goes into solution, you want to continue reacting for 60 minutes. After 60 minutes, you can precipitate the nitroguanidine by pouring it into water. Now, you can use room temperature water, that's okay. You will get a higher yield the colder the water is, because the solubility of nitroguanidine drops the colder the water is. So I usually just fill up a vessel with ice and then water and then dump off my solution into that. The nitroguanidine precipitates right away. It's going to be a white substance, a very kind of squishy, mushy type of material. It doesn't look at all like nitroguanidine yet. You're going to have to recrystallize it to get those nice needles that you're used to seeing. And then keep in mind that you want the quantity of water that you dump off into for precipitation to be pretty high. You really want quite a bit of water, and it's not going to hurt to have more. If you have too little water, you're not going to get as much precipitation. The water doesn't have to be anything special. You really don't even have to use distilled water, because nitroguanidine isn't ionically sensitive in any way. So you're not going to have problems using tap water. So your precipitated crude nitroguanidine is still quite acidic. Make sure you're still wearing gloves and eye protection, all that stuff. You now have to begin purification. It's pretty simple. You just heat water up to boiling and add nitroguanidine. You allow it to completely dissolve. If you have some nitroguanidine still in solution, you may need to add more water and boil it. The water should be totally clear, and then you just remove the vessel from heat and allow it to cool on its own, and you're going to get the precipitation of crystals. As for your end product, you just dry it out. You can either air dry it or apply a little bit of heat. I like to dry things typically around 60 C. So that's it for nitroguanidine. I'm not going to go into use. Maybe we'll do another video later on nitroguanidine 2. But I don't want to make this video too long because it's already entirely too long. So hope you enjoyed this one. Take care. Thanks for watching.